The telegram arrived at Grumman Aircraft's Bethpage, Long Island facility on June 19, 1944, and the words on the paper seemed to describe an impossibility. Lieutenant Commander John Thatch, aboard the USS Lexington in the Philippine Sea, had just witnessed something that defied every calculation the Navy's aviation experts had ever made. In a single day of aerial combat, American fighter pilots had shot down over 350 Japanese aircraft while losing fewer than 30 of their own. The ratio wasn't just favorable, it was annihilating. Navy brass initially suspected the combat reports were wildly exaggerated because no aerial battle in history had produced such lopsided results. But aircraft carrier deck logs, gun camera footage, and confirmed wreckage told the same story. Something extraordinary had happened in the skies over the Philippine Sea, and the weapon responsible was a fighter plane that American factories had been producing at a rate that seemed equally impossible. One complete F4F Hellcat rolling off the assembly line every 6 hours, around the clock, for over 2 years straight. The man who made that production miracle possible was standing in Grumman's Plant 2 when the reports came in. Leon Swirbul wasn't an engineer or a pilot, or even a production expert by training. He was a former barnstormer who'd crashed more planes than most people had seen, a self-educated manufacturing genius who'd worked his way up from riveter to factory floor manager to co-founder of the company. At 46 years old, Swirbul had spent 3 decades learning how aircraft were built by building them with his own hands. He understood aluminum the way surgeons understand flesh because he'd cut, shaped, and riveted enough of it to build a small air force by himself. When Pearl Harbor thrust America into total war, Swirbul faced a challenge that would have crushed lesser men. The Navy needed fighters desperately. The F4F Wildcat, Grumman's current production model, was outmatched by the Japanese Zero in nearly every performance category except survivability. Navy pilots were dying at rates that threatened to break American carrier aviation entirely. The fleet needed a new fighter, one that could outperform the Zero, and they needed it in numbers that seemed mathematically impossible given the reality of aircraft manufacturing in 1941. Traditional aircraft production was essentially handcraft manufacturing with industrial tools. Each plane was a unique creation assembled by skilled workers who understood the entire aircraft as an integrated system. A veteran aircraft builder could spend 40 hours on a single wing section, carefully fitting each rib, adjusting each skin panel, ensuring every rivet created a perfect aerodynamic surface. Quality came from expertise accumulated over years of apprenticeship. Speed came nowhere because it couldn't. Building fighters that way meant Grumman could produce maybe 40 Wildcats per month if they pushed hard. The Navy needed hundreds of the new design monthly, eventually thousands. The math didn't work. Swirbul spent the first weeks of January 1942 walking the production floor at 3 in the morning, when only the night shift worked and the factory's rhythms became visible without the chaos of peak operations. He watched veteran workers perform tasks with unconscious competence, their hands moving through sequences they'd repeated thousands of times. He noticed where the bottlenecks formed, which operations required waiting for previous steps, where tools were stored versus where they were needed. The inefficiencies were invisible in normal observation because they'd always been there. They were built into the very philosophy of how aircraft got made. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The insight that would transform everything came to Swirbul while watching a worker install control cables in a Wildcat fuselage. The man was simultaneously an expert and a bottleneck. He knew exactly which cables went where, could route them through the airframe's complex internal structure blindfolded, and had the judgment to spot problems before they became dangerous. But he was also one of maybe 15 people in the entire factory who could do that job. If he got sick, production stopped at that station. If he needed to train someone else, it took months. His irreplaceable expertise made him invaluable and made the production system fragile. Swirbul asked himself a question that seemed almost blasphemous to aviation traditionalists. What if the expertise could be built into the process itself rather than residing in the worker? What if anyone could install those cables correctly because the installation method was so carefully designed that errors became nearly impossible? It wasn't about de-skilling workers, it was about encoding expert knowledge into tooling, fixtures, and procedures so precisely that the work itself guided even novice hands toward perfection. The F4F Hellcat design, still being finalized in early 1942, became Swirbul's laboratory for testing this radical manufacturing philosophy. He worked directly with Grumman's chief designer, Leroy Grumman, making an unusual demand. Design the aircraft not just for performance, but for production. Every component needed to be manufacturable by workers with minimal training. Every assembly sequence needed to be logical and repeatable. The plane had to be designed so that building it was almost foolproof. This request created immediate tension with the engineering team. Aircraft designers optimized for performance, weight, and aerodynamics. They didn't traditionally worry about whether some rivet was easy to install because skilled workers would figure it out. Swirbul was asking them to add manufacturing constraints to their already complex design equations. Some engineers resisted, arguing that production concerns would compromise the fighter's combat effectiveness. Swirbul countered with brutal arithmetic. The best fighter in the world does nothing if you can only build 10 per month. A very good fighter built in hundreds per month wins wars. The compromise that emerged would prove revolutionary. The Hellcat would be designed with approximately 30% more internal volume than strictly necessary for its systems. This extra space meant workers had room to maneuver tools, could see what they were working on, and didn't need exceptional dexterity to complete assemblies. Weight increased slightly, but production speed would multiply. The wings used a standardized rib pattern that repeated across the span rather than unique ribs for each position. Slightly less aerodynamically pure, but infinitely easier to manufacture. Every fastener was designed to be installed from the outside whenever possible, eliminating the need for workers to contort themselves inside confined spaces. The gamble was enormous. The Hellcat was being designed to sacrifice some performance margin for production capability, betting that quantity and reliability would overcome whatever edge the Zero maintained in pure dogfighting metrics. Navy brass were skeptical. They'd been taught that fighter combat came down to pilot skill and aircraft performance. The idea that industrial capacity might be equally decisive seemed to miss the fundamental nature of air warfare. Swirbul knew something the naval aviators didn't fully appreciate yet. The Pacific War wouldn't be decided by individual dogfights, but by attrition across thousands of miles of ocean. Whoever could replace losses faster, train new pilots quicker, and maintain combat strength despite casualties would eventually overwhelm the other. The Zero was a masterpiece of aeronautical engineering, but it took Japanese factories 80 hours to build one. If Swirbul could get Hellcat production down to 20 hours, the math became unstoppable regardless of performance differentials. The contrast with Japanese manufacturing philosophy couldn't have been sharper. Japanese aircraft production was built on the same craft tradition that had produced samurai swords for centuries. Each Zero was essentially hand-built by highly skilled artisans who took professional pride in their work. The Mitsubishi factories in Nagoya employed workers who'd spent years mastering specific techniques. A senior airframe assembler might have 15 years of experience before being trusted with final assembly responsibilities. This expertise produced beautifully constructed aircraft with exceptional fit and finish, but it also meant production could never exceed what those irreplaceable skilled workers could accomplish. The Japanese had made a strategic calculation early in the war that turned out to be catastrophically wrong. They assumed the war would be short, decided by early victories that would demoralize American will. Under that assumption, quality and pilot skill mattered more than replacement capacity. Their best pilots, trained extensively over years, would destroy American aviators in combat. Their superior fighters would maintain air superiority through technical excellence. When America sued for peace after initial defeats, Japan's smaller but elite air force would have proven adequate. Every assumption in that calculation proved false. America didn't seek peace after Pearl Harbor. The nation's rage fueled industrial mobilization on a scale Japan's planners hadn't imagined possible. While Japanese factories struggled to increase Zero production from 25 to 30 units monthly per facility, American industry was preparing to produce aircraft like consumer goods. The fundamental difference wasn't resources or technology, it was manufacturing philosophy. Japan built weapons, America manufactured them. The distinction would prove decisive. The first production Hellcat emerged from Grumman's Bethpage facility in June 1942, exactly 8 months after the design was frozen. That timeline alone was revolutionary. Traditional fighter development took 2 to 3 years from design to production, but this first aircraft was essentially a hand-built prototype produced using traditional methods. It took over 200 worker hours to complete. Swirbul looked at that number and saw not achievement but challenge. If mass production was going to transform the Pacific War, he needed to cut that figure by 90%. The Pratt & Whitney R2800 double Wasp engine that powered the Hellcat represented both the aircraft's greatest strength and its most significant production challenge. This massive radial engine produced 2,000 horsepower, nearly double what the Zero's power plant generated. The power advantage gave the Hellcat performance margins that would prove decisive in combat. But the engine itself was a complex assembly containing over 1,200 individual parts. Each engine required precision machining to tolerances that made airframe construction seem crude by comparison. A single crankshaft took 43 separate machining operations to complete. Pratt & Whitney's engine production facility in East Hartford, Connecticut, faced the same transformation requirements as Grumman's airframe production. Traditional aircraft engine manufacturing relied on master machinists who'd spent decades learning their craft. A senior cylinder boring operator understood metallurgy, tooling wear patterns, thermal expansion effects, and dozens of other factors that affected final tolerances. That expertise produced excellent engines but couldn't scale to wartime requirements. Pratt & Whitney implemented their own fixture-based system, creating specialized tooling that guided even novice machinists through complex operations. The partnership between engine manufacturer and airframe producer became a critical element of Hellcat's success. Engine installation at Grumman exemplified the coordination challenges Swirbul faced. The R2800 weighed over 2,300 pounds, including accessories. It had to be precisely positioned within the fuselage mounting frame, connected to fuel lines, oil lines, cooling ducts, electrical systems, and control linkages. Any misalignment could cause vibration that would destroy the aircraft in flight. Traditional installation took skilled workers over 12 hours, constantly measuring and adjusting. Swirbul's team designed an overhead crane system with positioning jigs that guided the engine into exact placement. The crane movements were calibrated so precisely that workers simply activated motors, and the engine descended into perfect position. Installation time dropped to 90 minutes. The coordination between engine and airframe production schedules demanded precision that seemed almost impossible. Grumman needed exactly as many engines as they had aircraft to install them in, arriving precisely when installation stations were ready. Too few engines meant completed airframes waiting, wasting worker time. Too many engines meant expensive inventory, consuming warehouse space and capital. Swirbul established direct communication with Pratt & Whitney's production schedulers, synchronizing their output to within single-unit accuracy. Every week, both factories knew exactly how many units the other would produce, allowing planning that eliminated waste throughout the supply chain. The transformation of Grumman's manufacturing process began with what Swirbul called process mapping, though he never used that term. He had his floor supervisors document every single step involved in building a Hellcat, from the moment raw aluminum arrived until a finished fighter taxied under its own power. The list eventually contained over 12,000 individual operations. Most aircraft manufacturers would have looked at that number and seen inevitable complexity. Swirbul saw 12,000 opportunities for optimization. He grouped operations into categories. There were operations that required genuine skill and judgment, things like final control surface adjustment, where experienced hands could detect binding that instruments might miss. These would remain the domain of trained workers. Then there were operations that seemed to require skill but actually just needed proper tooling, like drilling holes for rivets at precise locations. Finally, there were operations that required no skill at all once properly structured, like installing pre-measured lengths of wire or attaching standardized brackets. The middle category, tasks that appeared skilled but weren't, became Swirbul's primary target. Take rivet installation. A skilled riveter could examine a blueprint, calculate the proper rivet pattern for a given structural load, select the correct rivet type from dozens of options, drill the hole to the exact depth for that specific skin thickness, and install the rivet with proper bucking pressure. All of that knowledge and judgment was encoded in the worker's expertise. An inexperienced person could take hours to do what the expert did in minutes, and would likely make errors requiring expensive rework. Swirbul's solution was drilling fixtures. These were precisely machined templates that clamped onto specific aircraft sections. The fixture contained pre-drilled guide holes at exactly the locations where rivets needed to go. The holes were sized so only the correct drill bit would fit. Color coding indicated which rivet type went into which hole. The worker's job became purely mechanical. Clamp the fixture, drill through the guide holes, install the indicated rivet type, remove fixture, move to the next section. No judgment required, no expertise necessary. The fixture contained all the expertise encoded in metal. Creating these fixtures was incredibly labor-intensive initially. Grumman's tool and die makers spent months building hundreds of specialized jigs for different Hellcat sections. Each fixture had to be machined to tolerances of 0.005 of an inch. The cost was staggering, over $400,000 for tooling alone, roughly equivalent to the price of 8 complete aircraft under traditional manufacturing. But once those fixtures existed, they could guide unlimited numbers of workers through perfect installations. The upfront investment would pay dividends across thousands of aircraft. The fuselage assembly process exemplified the transformation. Traditionally, workers would take a fuselage skeleton and gradually attach skin panels, drilling and riveting each panel in place, while constantly checking alignment. The process required experience to ensure the fuselage maintained its designed shape under the stress of assembly. Workers who rushed or made mistakes could produce fuselages with subtle twists or bends that would affect flight characteristics. Swirbul implemented what he called station assembly with overhead fixtures. The fuselage skeleton was mounted into a massive steel jig that held every structural member in perfect alignment. The jig was so precisely machined that components could only fit one way, the correct way. Skin panels were pre-drilled using templates before reaching the assembly area. Workers installed panels in numbered sequence, each panel having a designated position that was unambiguous. The overhead fixtures held each panel in perfect position while workers riveted. No skill required for alignment because the fixture enforced alignment automatically. The training implications were revolutionary. Under traditional methods, a fuselage assembler might need 18 months of apprenticeship to develop sufficient skill. Under Swirbul's system, workers could be productive after 3 weeks of training. They weren't learning aircraft construction as a craft. They were learning specific station tasks as repeatable procedures. A worker at Station 7 didn't need to understand the entire fuselage. They needed to master the 23 specific operations performed at Station 7, each operation guided by fixtures and documented in step-by-step procedures. This approach seemed to violate every principle of quality craftsmanship. Critics argued that workers who didn't understand the whole product couldn't possibly build it well. Swirbul's response was characteristically direct. He brought skeptics to the production floor, showed them aircraft built under the new system, and challenged them to identify any quality difference from traditionally built planes. They couldn't. The fixtures didn't just equal expert human judgment. They exceeded it by eliminating the variability that even experts introduced. By November 1942, with the new methods gaining traction, Hellcat production had climbed to 40 units monthly. Still far short of Navy requirements, but the trajectory was exponential rather than linear. Each month brought further refinements. Workers suggested improvements based on their station experience. A riveter noticed that reaching certain fasteners required awkward arm positions that slowed work. Engineers redesigned the fixture to provide better access. The cumulative effect of thousands of small optimizations began compounding. The Hellcat's distinctive folding wing design, essential for carrier storage, added another layer of manufacturing complexity that tested Swirbul's production philosophy to its limits. Each wing had to fold precisely at a specific hinge point, with locking mechanisms that would hold under combat maneuvering stresses exceeding 7 times the force of gravity. The folding mechanism contained over 40 individual components, including pins, locks, springs, and structural hinges. Any misalignment in the fold mechanism could cause the wing to fail catastrophically during flight maneuvers or refuse to unfold properly for combat operations. Traditional wing fold mechanism assembly required senior technicians who understood the precise adjustment required for reliable operation. These workers could feel whether a mechanism was properly aligned through subtle resistance patterns as they moved components. That tactile expertise came from years of experience and couldn't be taught in classroom sessions. Swirbul's approach was to eliminate the need for that expertise entirely by making the mechanisms self-aligning through clever engineering. The engineering team redesigned the fold mechanism with positive positioning features that forced components into proper alignment when assembled. Pinholes were machined to stepped tolerances that only allowed insertion in the correct orientation. Springs were pre-tensioned during manufacturing, so workers simply installed them without adjustment. The locking pins featured chamfered edges that guided them into engagement automatically. What had been an adjustment-intensive assembly became a purely mechanical installation where components either went together correctly or didn't go together at all. Workers didn't need to feel whether something was right. The design made wrong assembly physically impossible. Testing the fold mechanisms became automated as well. Every completed wing went through a cycling fixture that folded and unfolded the wing structure 50 times while measuring force loads and positioning accuracy. Any mechanism that deviated from specifications was caught immediately before the wing joined a fuselage. The testing fixture itself required no human judgment. It automatically compared measured values against acceptable ranges and flagged any deviations for technician review. Quality control became as systematic as production itself. The workforce transformation happened simultaneously. Grumman's pre-war employment of 6,000 workers, mostly skilled craftsmen, would need to expand to over 25,000 to meet production targets. The Long Island labor pool of experienced aircraft workers was exhausted almost immediately. Swirbul began recruiting anyone willing to work, regardless of background. Former secretaries, recent high school graduates, housewives whose husbands had shipped overseas, retired workers coming back to contribute. The common factor wasn't skill. It was willingness to learn specific procedures and perform them repeatedly with precision. The training system Swirbul developed was almost military in its structure. New workers spent their first week in classroom sessions learning about the Hellcat as a complete system, not because they'd need that knowledge for their jobs, but because Swirbul believed understanding the whole product created pride that improved performance. Then came station-specific training, where workers learned their exact tasks under the supervision of experienced trainers. The first week on the actual production line, each new worker had a mentor standing beside them, correcting mistakes before they propagated. Quality control evolved into a distributed system rather than a final inspection process. Under traditional manufacturing, inspectors checked finished aircraft, finding problems after they'd been built into the product. Correcting those problems required disassembly, rework, and reassembly, sometimes taking longer than the original construction. Swirbul implemented in-process inspection, where quality checks happened at every station before work proceeded to the next step. A misdrilled hole caught at Station 12 could be corrected in 5 minutes. The same error discovered during final inspection might require 8 hours of rework. The inspection system grew increasingly sophisticated as production scaled. Swirbul hired former teachers to develop inspection training programs because they understood how to communicate standards clearly to non-technical workers. Every inspector learned not just what to check, but why those checks mattered. They understood that a rivet in the tail section could lead to flutter that would destroy the aircraft at high speed. That understanding transformed inspection from routine checking into critical quality assurance. The inspection tools themselves evolved to match production speed requirements. Traditional aircraft inspection used standard measurement tools like calipers and straight edges. These worked fine when inspectors had unlimited time, but became bottlenecks in rapid production. Grumman's tool engineers developed go-no-go gauges specific to Hellcat tolerances. An inspector didn't measure a dimension and calculate whether it was acceptable. They simply inserted the gauge, which would fit if the part was correct and wouldn't fit if it was wrong. Binary decisions replaced calculations, and inspection speed matched production pace without sacrificing accuracy. Statistical tracking transformed quality control from reactive to predictive. Every defect was logged with its location, nature, probable cause, and the station where it occurred. Production managers analyzed these statistics daily, looking for patterns that indicated emerging problems. If Station 14 showed increasing rivet failures on Thursday afternoons, investigation might reveal the air compressor serving that station was overheating after extended use. Fixing the compressor prevented hundreds of future defects. The system didn't just catch problems. It eliminated root causes before they generated failures. The statistical results began telling a story that even skeptics couldn't ignore. Rework rates dropped from an industry standard of 12% to under 3%. Production time per aircraft fell from 200 hours to 150 hours by early 1943, then to 120 hours by summer. Each optimization cascaded into others. Faster production meant more learning opportunities. More learning meant better procedures. Better procedures meant even faster production. The virtuous cycle Swirbul had envisioned was becoming reality. But the Navy's demands kept escalating. The Pacific War was consuming aircraft at rates that exceeded even pessimistic projections. Carrier battles at Coral Sea and Midway had proven that naval air power would decide the Pacific theater. The service wanted 500 Hellcats monthly, then revised that to 600, eventually pushing for 800. Each increase seemed to push against the physical limits of what a single factory could produce. Grumman's Bethpage facility covered 75 acres, employed over 20,000 workers, and operated 3 shifts around the clock. Where would the additional capacity come from? Swirbul's answer demonstrated that his production genius extended beyond factory floor optimization. He proposed what he called the dispersed manufacturing model. Instead of building complete Hellcats at Bethpage, Grumman would establish satellite facilities across Long Island, each specializing in specific major assemblies. One plant would build nothing but wings, another would produce fuselages. A third would handle engine installations and final assembly. The main Bethpage facility would become primarily a coordination and final integration center rather than a complete manufacturing operation. The logistics seemed nightmarish, coordinating multiple facilities, transporting major assemblies, synchronizing production schedules across sites. Traditional aviation wisdom said this would create chaos, but Swirbul had spent enough time studying automotive manufacturing to understand that Ford and General Motors had been doing exactly this for decades. The key was standardization so absolute that components from different facilities mated perfectly every time. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Grumman established what became known as the Iron Works Network. Plant 2 inches Bethpage handled fuselage construction. Plant 3, a converted automobile dealership in Farmingdale, produced wings. Plant 14, formerly a laundry facility, manufactured control surfaces. By late 1943, the network included 21 separate facilities, some as small as converted warehouses, each contributing components to the overall production flow. Transportation between facilities became its own specialized operation. Major assemblies like wings and fuselages couldn't be shipped like ordinary cargo. They required custom trailers with pneumatic suspension systems that absorbed road vibrations which might stress airframe structures. The routes between plants were surveyed to ensure trucks could navigate without tight turns that would damage overhanging components. Some roads were actually widened by the county specifically to accommodate Grumman's transport needs, a testament to how critical the production was considered to the war effort. Each transport vehicle carried a specially trained escort who understood the assembly being moved. If a wing assembly hit an unexpected road obstacle, the escort had authority to stop the convoy and inspect for damage. Even minor dents or stress marks meant the assembly returned to its originating plant for inspection and possible rework. The cost of rejecting a completed major assembly was enormous, but the cost of installing a damaged assembly into a combat aircraft was unthinkable. Escorts took their responsibility with grave seriousness, knowing that carelessness on Long Island roads could kill pilots over the Pacific. Weather became an unexpected production variable in the dispersed system. Rain didn't stop manufacturing at individual facilities, but it could halt transport between them. Uncovered assemblies couldn't travel in precipitation without risking corrosion in unpainted areas. Winter brought additional challenges as freezing temperatures affected rubber gaskets and seals if assemblies sat too long during transport. Swirbul established heated transport sheds at pickup and delivery points so assemblies never waited exposed to weather. The attention to such details separated his operation from manufacturers who focused only on building rather than the complete production system. The standardization requirements became almost obsessive. A wing built in Farmingdale had to attach to a fuselage built in Bethpage with the same precision as if both were constructed side by side. Tolerances were specified to 10,000ths of an inch. Testing fixtures traveled between plants, so each facility could verify their assemblies met identical specifications. If a wing didn't fit perfectly to a fuselage, the entire production philosophy collapsed. The pressure on quality control was immense. The coordination system Swirbul developed anticipated modern supply chain management by decades. Each facility operated on the same production clock. At any given moment, every plant knew exactly which components were due at final assembly and when. Trucks carrying wings left. Farmingdale precisely on schedule. Fuselages completed at Bethpage moved to integration exactly as planned. If any facility fell behind, the ripple effects threatened the entire network. Swirbul installed dedicated telephone lines between plants so supervisors could communicate instantly when problems arose. The human element of managing this distributed workforce proved equally challenging. Over 25,000 workers across multiple sites, most of whom never saw a complete Hellcat emerge, needed to understand their contribution to the war effort. Swirbul instituted what he called victory visibility programs. Photos of Hellcats in combat were posted throughout every facility. Pilots who'd flown Grumman fighters visited plants to thank workers personally. When reports arrived of aerial victories, the specific aircraft serial numbers were traced back to which facilities had built their components, and those workers received recognition. A wing built by Mary Thompson in Farmingdale had helped Lieutenant Junior Grade Alex Vrasiu shoot down his 19th enemy plane. That connection transformed abstract manufacturing into personal contribution. The production numbers climbed in ways that seemed to defy physics. January 1943 saw 130 Hellcats delivered. By June, that number reached 300. September hit 450. December pushed past 500 monthly. Each Hellcat contained approximately 48,000 parts, 600 pounds of special alloys, 200 feet of control cables, and miles of electrical wiring. Every component had to be manufactured, inspected, assembled, tested, and shipped in perfect coordination. The fact that the system worked at all was remarkable, that it worked flawlessly enough to produce a complete combat aircraft every 4 hours by late 1943 bordered on miraculous. The engineering refinements continued even as production accelerated. Swirbul established a unique feedback loop between combat pilots and factory workers. When aviators reported problems, those reports reached the production floor within days rather than months. One persistent complaint involved the cockpit canopy. Pilots reported that the existing design created blind spots that could prove fatal in combat. Grumman engineers redesigned the canopy with a bubble configuration, providing near 360-degree visibility. But redesigning a major component normally meant retooling production, which would slow output. Swirbul's production team figured out how to phase in the new canopy design while maintaining production speed. For 3 weeks, Hellcats rolled off the line with both old and new canopy types as the transition completed, but output never faltered. The fuel system modification demonstrated similar agility. Early Hellcats had experienced fuel tank fires when hit by enemy rounds. Not surprising given that aviation fuel is essentially controlled explosive, but unacceptable in combat aircraft. Engineers developed self-sealing fuel tanks lined with special rubber that would swell to close bullet holes. Implementing this change across all fuel tank locations required modifying 15 different assembly stations. Swirbul's team accomplished the transition in 4 weeks without reducing production rates. The next month's Hellcats all featured the improved tanks. Pilots started calling their planes the aluminum clouds, because they seemed to absorb punishment that would destroy lesser fighters. Material shortages threatened to derail everything in mid-1943. Aluminum was being consumed across the entire American war effort, from aircraft to ships to vehicles. The specific alloy used in Hellcat wing spars, chosen for its perfect balance of strength and workability, became temporarily unavailable when the primary supplier diverted production to B-17 bomber requirements. Traditional aircraft manufacturers would have halted production awaiting material. Swirbul's team analyzed alternative alloys overnight, tested samples, and qualified a replacement within 72 hours. Production paused for exactly 1 shift, while new alloy specifications were distributed to affected stations. No other interruption occurred. The night shift became the legendary backbone of Hellcat production. 3 shifts worked around the clock because Pacific battle zones were 12 time zones away and couldn't wait for American daylight hours to pass. The night crew, working 11 in the evening to 7 in the morning, developed their own culture and pride. They called themselves the Ghost Builders because their work happened while most of Long Island slept. Production records showed the night shift actually exceeded day shift output by 3%. Likely because fewer interruptions and management visits meant workers could focus entirely on their stations. By January 1944, the production system had achieved what Swirbul had envisioned, but even he had doubted was fully achievable. 1 complete F6, F3 Hellcat every 6 hours. The number was so consistent that Navy procurement officers could predict exactly how many aircraft would be available for specific carrier deployments months in advance. The reliability of production became as much a strategic asset as the aircraft themselves. Fleet commanders could plan operations, knowing reinforcements would arrive on schedule, because Grumman's production had become as reliable as gravity. The financial implications were equally stunning. Traditional aircraft manufacturing cost curves showed decreasing costs as production increased, but the improvements were typically measured in single-digit percentages. Grumman's Hellcat production showed cost reductions of over 40% from first production unit to 1000th production unit. The learning curve wasn't just faster, it was fundamentally steeper because the entire production philosophy was designed to improve continuously. Each aircraft built contained lessons that made the next one cheaper and faster to produce. Navy pilots receiving Hellcats in the Pacific could feel the production quality in their machines. Unlike some mass-produced equipment that suffered from rushed assembly, Hellcats consistently arrived in better condition than their predecessors. The fixtures and controlled processes eliminated the variability that even skilled workers introduced. 2 Hellcats built weeks apart and thousands of serial numbers distant flew identically because they were constructed using identical procedures by workers following identical specifications. This consistency meant pilots could trust their aircraft completely, knowing the machine would perform exactly as designed every time. The combat results validated everything Swirbul had believed about quantity and quality, being complementary rather than opposed. In 1943, Hellcats achieved a kill ratio of 11-1 against Japanese aircraft. By 1944, with production improvements implemented into combat modifications, that ratio climbed to 19-1. Pilots weren't just getting adequate fighters fast, they were getting excellent fighters fast. The Hellcat could outclimb the Zero above 14,000 feet, outdive it at any altitude, outroll it in combat maneuvers, and take devastating punishment while protecting its pilot. These weren't compromise attributes forced by production constraints. They were carefully engineered capabilities that happened to be achievable through mass production methods. Lieutenant Commander Edward Butch O'Hare had proven the Hellcat's combat capability in its earliest deployments. Flying from the USS Independence in August 1943 during raids against Marcus Island, O'Hare and his wingmen encountered aggressive Zero fighters defending the Japanese base. The engagement became a laboratory test of Hellcat versus Zero in actual combat conditions. O'Hare discovered that his aircraft could trade energy with the Zero in ways the Wildcat never could. When a Zero attempted its famous climbing turn, O'Hare's Hellcat could follow, something that would have been suicide in earlier American fighters. The power advantage and superior high-altitude performance gave American pilots tactical options that changed the entire psychology of Pacific air combat. The armament improvements reflected the feedback loop between combat experience and production capability. Early Hellcats carried the same 650 caliber machine guns as the Wildcat, adequate against lightly armored Japanese aircraft. But pilots reported that sometimes targets absorbed incredible amounts of fire before going down. The Zero's aluminum structure was surprisingly robust when bullets passed through without hitting vital components. Engineers responded by optimizing ammunition feed systems for higher sustained firing rates and improving the gun convergence pattern to concentrate fire more effectively at optimal combat ranges. These modifications were implemented into production without slowing output because they'd been designed with producibility in mind from the start. The Hellcat's ability to absorb combat damage became legendary among carrier aviators. Lieutenant Junior Grade Stanley Vaitasser returned to the USS Enterprise after an engagement over the Gilberts with 247 bullet holes in his aircraft. The self-sealing fuel tanks had closed after multiple penetrations. The armor plate behind his seat had stopped rounds that would have killed him. The robust airframe structure had maintained integrity, despite damage that would have caused structural failure in lighter aircraft. Vaitasser's Hellcat was repaired overnight by carrier maintenance crews and flew the next morning's mission. That survivability meant pilots who would have died in other aircraft returned to fight again, their experience compounding American combat effectiveness. The Battle of the Philippine Sea in June 1944 became the ultimate vindication. American carrier task, forces launched massive fighter sweeps, specifically to draw out Japanese aviation assets and destroy them. The strategy relied entirely on having enough fighters to absorb initial losses while maintaining overwhelming numbers. Over 450 Hellcats participated in the battle, roughly what Grumman produced in a single month at that point. Japanese losses exceeded 350 aircraft in what pilots called the Great Marianas Turkey Shoot. The attrition mathematics Swirbul had understood from the beginning had become combat reality. Japan simply couldn't replace those losses, while America could replace everything expended within weeks. The production achievements continued accelerating through mid-1944. Peak output reached 664 Hellcats in a single month, over 20 aircraft daily. At certain moments, a Hellcat was rolling off Grumman assembly lines every 3.5 hours. The number defied belief. Each aircraft represented 20,000 separate manufacturing operations performed flawlessly in sequence by thousands of workers across multiple facilities coordinated to precision tolerances. Yet the machines kept emerging at metronomic pace, identical in quality, ready for combat, needing only fuel and pilots to become weapons. Japanese military intelligence struggled to comprehend the reports they received about American fighter production. Their analysis suggested that either American factories were exaggerating numbers or they were producing inferior aircraft that would fail in combat. The Zero remained the superior dogfighter in their assessment, and Japanese production methods emphasized quality through craftsmanship. When intelligence finally confirmed both the production rates and the combat effectiveness, the implications were devastating. Japan's aviation industry was producing roughly 1,800 fighters monthly across all types in 1944. America was producing over 8,000 monthly, with Hellcats alone approaching 700. The numerical advantage was nearly 5-to-1 before considering the superior training, fuel availability, and logistical support American pilots enjoyed. The tragedy of Japanese aviation planning became apparent in their pilot replacement program. Experienced Japanese aviators who trained for years were being killed faster than the training system could produce replacements. By late 1944, some Japanese replacement pilots arrived at carrier squadrons with barely 100 flight hours compared to the 300-plus hours American aviators received before combat assignment. These green pilots faced Hellcat veterans who'd learned combat tactics from instructors who'd survived years of Pacific fighting. The experience gap compounded the equipment disparity into a cascade of failure that made Japanese aerial resistance increasingly futile. The Battle of Leyte Gulf in October 1944 demonstrated the total nature of American air supremacy achieved through production dominance. Japanese naval aviation launched desperate attacks against American invasion forces supporting the Philippines campaign. Hellcats from multiple carrier groups intercepted the attacks in waves. Commander David McCampbell, leading Air Group 15, encountered a massive Japanese strike force of over 60 aircraft. His small Hellcat flight shot down over 20 enemy planes while suffering no losses. McCampbell personally destroyed 9 aircraft in that single engagement, an American record that still stands. Such lopsided results became routine rather than exceptional, direct evidence of what happens when production capacity enables tactical dominance. The kamikaze threat that emerged in late 1944 tested Hellcat capabilities in unexpected ways. Japanese pilots deliberately crashing their aircraft into American ships represented desperate tactics from a force that knew it couldn't win conventional battles. But even suicide attacks required reaching the targets, and Hellcat combat air patrols made that increasingly difficult. The fighters' speed and armament allowed them to intercept kamikazes at distances where even successful interception gave the Japanese aircraft minimal chance of reaching ships. Fleet air defense became so effective that American carriers suffered fewer kamikaze hits, despite the increased intensity of Japanese suicide operations. The worker pride at Grumman facilities became almost palpable by late 1944. Production boards in each facility tracked cumulative output with growing totals displayed prominently. When the 5,000th Hellcat was completed in August 1944, the celebration involved workers from every shift gathering to watch the aircraft taxi out for its first flight. Pilots returning from the Pacific specifically visited Grumman plants to share combat stories, and workers listened with the intensity of people who understood their daily labor had direct life and death consequences. Letters from carrier squadrons adorned factory walls, thanking specific work groups for the quality of their aircraft. The F6F5 variant that entered production in 1944 incorporated lessons from over a year of combat operations. The new model featured improved armor protection, strengthened wing structure for higher dive speeds, and better weapons targeting systems. Under traditional manufacturing, introducing a new variant would have meant significant production disruption. Swirbul's system absorbed the changes with barely a ripple. The modular production approach meant only affected stations needed retraining. Workers at unchanged stations continued their tasks identically. Within 3 weeks of the variant's introduction, production speeds had recovered to previous levels, then exceeded them as workers mastered the new procedures. The final production numbers tell a story that transcends mere manufacturing statistics. Between June 1942 and November 1945, Grumman produced 12,275 Hellcats. Over 12,000 complex combat aircraft, each containing 48,000 parts, assembled to specifications demanding tolerances of thousandths of inches. The production happened primarily at facilities on Long Island using a workforce that had been largely untrained for aircraft manufacturing when the war started. These workers, guided by Swirbul's fixture-based system, had built more of a single fighter type than any other American manufacturer had built of any design during the entire war. The Iwo Jima campaign in February 1945 showcased how Hellcat production superiority translated into tactical flexibility impossible for resource-constrained Japanese forces. American carrier groups launching strikes against the island maintained continuous combat air patrols, rotating Hellcat squadrons, so fresh aircraft were always airborne. A typical day saw over 200 Hellcat sorties from the combined fleet, each aircraft flying multiple missions before maintenance requirements grounded them. Japanese defenders faced an unending stream of American fighters that suppressed any attempt at aerial resistance. The island's airfields, designed to support defensive fighter operations, became targets rather than bases because Japanese aircraft couldn't survive to use them. Ground attack missions revealed another dimension of Hellcat production impact. Carrier air wings could afford to use their fighters for close air support because they had enough aircraft to simultaneously maintain fleet defense. Hellcats loaded with rockets and bombs pounded Japanese positions supporting marine advances. When aircraft were lost to ground fire, replacements arrived on escort carriers specifically assigned to replenish losses. An American air group that lost 20 aircraft in a week received full replacements within days. Japanese ground forces had to contend with aerial attacks they couldn't stop because the defense resources that might have protected them had been destroyed in earlier air battles. Okinawa became the ultimate test of industrial warfare. The campaign, lasting from April through June 1945, saw the most intense aerial combat of the Pacific War. Japanese forces launched over 1,900 kamikaze sorties against American naval forces, supporting the invasion. Hellcat pilots flew exhausting combat air patrol schedules, some days logging over 8 hours of flight time across multiple missions. Aircraft wore out faster than normal combat operations would have caused due to the sustained high-performance flying. Carrier maintenance crews worked around the clock to keep maximum fighters operational. The attrition at Okinawa would have crippled any air force lacking production depth. American carrier groups lost over 400 aircraft during the campaign to combat damage, operational accidents, and mechanical failures. Pre-war aviation doctrine would have considered those losses catastrophic, requiring withdrawal for reconstitution. But replacement aircraft arrived continuously from escort carriers and transport ships. Fresh Hellcats, straight from Grumman production lines, were being assembled at rear area bases and ferried forward. The losses represented consumption of war material rather than irreplaceable capability destruction. Japanese forces, watching American air strength remain constant despite their attacks, faced the demoralizing reality that they were fighting production capacity they couldn't match regardless of their combat determination. The combat record those Hellcats compiled remains unmatched in aviation history. Navy and Marine pilots flying F4F Hellcats were credited with 5,223 aerial victories, representing over 75% of all Navy aerial kills during the Pacific War. 305 pilots became aces flying Hellcats, scoring 5 or more kills. Commander David McCampbell alone downed 34 enemy aircraft in his Hellcat, the highest total for any American naval aviator in history. The Hellcat's kill ratio exceeded 19-1 across all combat theaters. These weren't statistics of a marginally acceptable fighter rushed into production. They were numbers representing genuine aerial superiority, achieved through the combination of sound design, relentless production improvement, and industrial capacity applied with precision. The methodology Swirbul pioneered didn't remain confined to Grumman's operations. Navy procurement officials, impressed by the Hellcat production achievements, began requiring other manufacturers to adopt similar approaches. The Vought F4U Corsair, another excellent fighter that had struggled with production inefficiencies, saw its output double after implementing Grumman-style fixture-based manufacturing. The broader American aviation industry learned that mass production and high quality weren't opposites but complementary achievements when properly systematized. The transition to peace production after August 1945 created a different kind of challenge. Grumman's workforce of 25,000 workers had skills specifically developed for Hellcat production. Those skills didn't translate directly into civilian aviation manufacturing, which used different methods and materials. Swirbul faced the difficult task of maintaining employment while shifting production. Some workers moved into the Grumman Gulfstream civilian aircraft program, which adapted wartime production techniques for business aviation. Others found their skills valued across American manufacturing, as companies sought workers experienced in systematic production methods. The Long Island facilities that had hummed with Hellcat production fell gradually quiet through late 1945 and 1946. Plant by plant, the distributed network that had orchestrated 12,000 fighters consolidated back to core operations. Some facilities returned to their pre-war purposes. The former laundry that had produced control surfaces became a fakes laundry again. The automobile dealership that had built wings sold cars once more. But the workers who'd staffed those facilities carried their experience into post-war America, spreading Swirbul's production philosophy into industries he'd never imagined affecting. Post-war industrial historians would study Grumman's Hellcat production as a case study in manufacturing transformation. The lessons Swirbul had empirically developed anticipated formal production theories that wouldn't be articulated for decades. His emphasis on process standardization, worker training systems, distributed manufacturing coordination, continuous improvement loops, and quality built into production, rather than inspected afterward, all became cornerstones of modern industrial production. The specific innovations Swirbul introduced would reappear in manufacturing theory under different names. His fixtures that encoded expert knowledge into tooling became the concept of mistake-proofing, known in Japanese manufacturing as poka-yoke. His in-process quality checks were formalized as statistical process control. His worker suggestion system that captured frontline improvements was codified as continuous improvement or Kaizen. His distributed manufacturing coordination anticipated modern supply chain management. Swirbul had developed these approaches through practical necessity, years before academics gave them formal names and theoretical foundations. The human legacy proved equally significant. Over 25,000 workers passed through Grumman's wartime facilities, many of them women entering industrial work for the first time. These workers learned not just specific aircraft manufacturing tasks, but broader industrial skills that transferred into post-war careers. The training systems developed for Hellcat production became templates for workforce development programs across American industry. The idea that complex manufacturing could be broken into learnable components accessible to workers without extensive prior training revolutionized industrial education. Individual workers carried the experience forward in ways that rippled through American industry for generations. Margaret O'Brien had been a department store clerk before joining Grumman's electrical assembly team in 1943. She spent 2 years wiring Hellcat instrument panels, learning to follow wiring diagrams and solder electrical connections to exact specifications. After the war, she took those skills into the emerging television manufacturing industry, becoming a production supervisor responsible for training new workers in assembly techniques directly descended from what she'd learned at Grumman. Her workers didn't know their training methods traced back to fighter production, but the systematic approach she'd absorbed in the war years shaped how they learned their craft. Thomas Rodriguez started at Grumman in 1942 as a 17-year-old, fresh from high school. He began at the sheet metal cutting station, learning to operate shears that cut aluminum to precise dimensions. His supervisor, recognizing his aptitude, moved him progressively through more complex stations until he was assisting with final assembly coordination. The war ended before he finished college, but he'd accumulated more practical manufacturing knowledge than most engineering graduates. He eventually became a production engineer for a major appliance manufacturer, applying Swirbul's principles to refrigerator and washing machine production. When his company achieved quality levels that surprised industry competitors, Rodriguez traced the methods back to lessons learned building Hellcats. Dorothy Washington had been one of the first African-American women hired into Grumman's wing assembly team, a breakthrough that reflected both wartime labor demands and the gradual expansion of industrial opportunities. She specialized in the precise alignment procedures for wing skin panels, developing an expertise that made her station one of the fastest on the line. After the war, she used her experience to break into the emerging electronics assembly industry, eventually training workforces at multiple companies in the systematic methods she'd mastered at Grumman. The fixture-based approach worked equally well for circuit board assembly as it had for airframe construction, proving the methodology's transferability across manufacturing domains. Leon Swirbul received relatively little public recognition for his contributions despite their significance. He wasn't an engineer with patents, a pilot with victories, or an executive with political connections. He was a production genius whose work happened on factory floors rather than in boardrooms. His legacy lived in the 12,000 fighters that helped America achieve air superiority, in the thousands of workers he trained, in the manufacturing methods he pioneered, and in the lives saved because reliable aircraft reached combat zones when needed. The Hellcat production achievement demonstrated something profound about American industrial capacity that enemies and allies alike hadn't fully appreciated. The nation's strength lay not just in natural resources or population size, but in the ability to organize production at scale while maintaining quality. Other nations could design excellent weapons. Others could train skilled workers. But combining design, production, training, and logistics into integrated systems that delivered combat-ready weapons in overwhelming numbers required an industrial culture that America possessed uniquely. The broader implications extended beyond military production into how Americans approached complex manufacturing challenges. The can-do spirit that had characterized frontier expansion found new expression in industrial systematization. Workers who'd never built anything more complex than furniture were assembling fighter aircraft through the power of well-designed systems. The passer of the achievement wasn't individual genius but collective organization, the insight that properly structured processes could accomplish what seemed impossible. That insight would drive American manufacturing dominance for decades after the war ended, manifesting in automobiles, appliances, electronics, and eventually computers. Each industry learned from the wartime manufacturing revolution that Swirbul had helped pioneer. Japanese military leaders, conducting post-war assessments, consistently identified American production capacity as the decisive factor in the Pacific War. Superior fighters meant nothing when they couldn't be produced fast enough. Excellent pilots meant nothing when they couldn't be replaced. Strategic brilliance meant nothing when logistics couldn't support operations. America won the Pacific War in its factories as much as on its battlefields, and the Hellcat production achievement epitomized that industrial supremacy. The 6-hour Hellcat production cycle wasn't just a manufacturing record. It was the moment industrial capacity became a weapon as decisive as any mounted on the aircraft themselves. Every Hellcat that rolled off the line represented the accumulated effort of thousands of workers executing precisely coordinated tasks across dozens of facilities, all orchestrated by a former barnstormer who understood that wars are won not by building the best weapons, but by building enough excellent weapons to overwhelm any enemy. Leon Swirbul proved that mass production and quality weren't opposing forces, but complementary achievements, when genius applied itself to process as intensely as engineers applied themselves to design. The Pacific sky filled with Hellcats because a factory floor genius understood that the right system, properly implemented, could make the impossible merely routine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.